Swayam Prabha. Digital India. Educated India.
Hello everybody, welcome to today's lecture on material balance calculations for systems which have reactions and multiple units. Why multiple units? As I had mentioned already, most industrial processes require multiple units. You very rarely see a single unit process in an industrial scale. So this means we also need to learn how to perform material balance calculations for multi-unit processes. And in case of processes with reactions, you usually have a reactor which is fed with the reactants. In many cases, these reactants might have to be pre-processed. They might have to be mixed or they might have to be treated before they can be sent to the reactor, and this could be a step or a unit ahead of the reactors. You could also have downstream operations down the reactor which could require the purification of the product. Any product you ultimately want to sell in the market would have to meet certain standards. So it might be because of purity, it might be because of certain quality control. There might be different reasons for making sure that the final product is of a certain grade, and this can be accomplished only by separation processes which will follow the reactants. So as we mentioned earlier, no reaction goes to completion in an industrial setup, which means you will have a mixture of reactants and products which have been formed. So to get a pure product which can be sold, you will have these downstream operations, and you might also want to recover the reactants and reuse them. The reactants are going to cost money, which means the industry would not want to throw them away. So to recover these reactants is also a critical aspect for any process. So for these reasons, we always have downstream operations. So these separation processes would also have to be considered while we perform material balance calculations. Here we will perform a few example problems which take these things into account. So here is the first example problem. Metallurgical grade silicon is purified to electronic grade for use in semiconductor industry by chemically separating it from its impurities. The silicon metal reacts in varying degrees with hydrogen chloride gas at 300 degrees Celsius to form several polychlorinated silanes. Trichlorosilane is a liquid at room temperature and is easily separated by fractional distillation from the other gases. If 100 kilograms of silicon is reacted as shown in the figure, how much trichlorosilane is produced? So the process is given. As I had mentioned earlier, here you have a reactor and a downstream operation which is the distillation column. So silicon which is coming into the reactor reacts with hydrogen chloride gas to form different silanes, and trichlorosilane, which becomes a liquid at room temperature, is separated through the distillation process, and the rest of the material leave as volatile gases. So this is what the system gives. Now let us see how we can go about solving this material balance problem. For any material balance problem, the first step is to identify the basis. The problem statement clearly gives 100 kilograms of silicon being treated. So taking that into consideration, we will take the basis as 100 kilograms of silicon fed to the reactor. So basis is 100 kilograms of silicon solid in the feed which is B, so which is this feed. Now we can write different balance equations. So here we need to calculate the amount of trichlorosilane that is produced. So for doing this, we could either write component balances or we can write atomic balances. So here I have chosen to write atomic balances instead of molecular species balances. So what atomic balances can we write? So for this system we can write silicon balance, chlorine balance and hydrogen balance. As we have mentioned earlier, for atomic balances you do not have a generation or consumption term, and accumulation would be 0 at steady state. So, all these equations will be simplified to input equals output. So, all these three would be input equals output only. Now, let us start writing the balance equation for silicon. So, silicon is entering as silicon solid through the feed B. So, here what is the system we want to choose? Unlike the previous problems, we do not have only the reactor. So, we have a reactor and a distillation column. So, we need to identify the system we would want to start with. Here we have the information regarding the feed which is entering into the reactor, and we also have the information about the products which are leaving the distillation column. However, we do not have information about the stream which is connecting the reactor to the distillation column. So, this means taking the overall system would be the most appropriate way to approach the problem. Considering the overall system, the silicon balance can be written as, for the overall system, silicon balance is input equals output. So, input of silicon is only through the stream B, which is 100 kilograms of silicon. So, the basis has been taken as 100 kilograms of silicon based on the information given in the problem. However, if you see the composition of the stream which is leaving the reactant, leaving the distillation column, you find that the composition is given in terms of mole percentages. It is a gas, and conventionally the composition is given as mole percentages, which is what has been followed here also. This means using masses for silicon would require the mole percentages to be converted to mass percentages. Instead, we can also convert the basis of silicon, which is in 100 kilograms, to moles, so that we can use that directly. So, for this reason we will convert the mass of silicon into moles, which will give it as the amount of silicon in B would be equal to 100 divided by 28, which is the molecular weight, giving us 3.571 kilomoles. So, 3.571 kilomoles of silicon is being fed to the system. So, now for the output, you have silicon leaving in the form of H2SiCl2, SiCl4 and HSiCl3. So, all of these molecules have one atom of silicon. So, taking the mole percentages and the number of atoms of silicon per molecule, we can write the output as 0.2142 times 1 times D, which is the number of atoms of silicon leaving per molecule of H2SiCl2 in the stream D, plus you have 0.1429 times 1 times D, which is the number of atoms of silicon leaving per molecule of SiCl4 in the stream D, plus 1 times E, which is the number of atoms of silicon leaving through the trichlorosilane, which is HSiCl3, leaving through the stream E. So, substituting this back into the silicon balance, we get 3.571 equals 0.2142 D plus 0.1429 D plus E. So, the equation simplifies as 0.3571 D plus E equals 3.571. So, let us call this as equation 1. Now, we can write a balance for chlorine. So, the chlorine balance would be input equals output. Again, we have chlorine entering through the stream as entering to the system as HCl. So, you have one atom of chlorine per molecule of HCl. So, taking that into consideration, the input term becomes 1 times A, and you have output of chlorine in the form of H2SiCl2 SiCl4 and HSiCl3. So, you have 2 atoms of chlorine leaving through H2SiCl2. So, that is 2 times 0.2142 times D plus 4 times 0.1429 times D, which is the number of atoms of chlorine leaving in the form of SiCl4. You have 4 atoms of chlorine leaving per molecule of SiCl4 through the stream D, and you also have 3 atoms of chlorine leaving through the stream E in the form of HSiCl3. So, we have 3 times 1 times E. So, this equation then can be simplified as A equals D plus 3E. So, let us call this equation number 2. So, next we can write the balance equation for hydrogen. The hydrogen balance again, which is input equals output, using the same principles we have used till now. Input for hydrogen would be 1 times A equals 2 times 0.2142 times D plus 2 times 0.6429 times D plus 1 times E. So, this equation can be simplified as A equals 1.7142 D plus E. So, this would be equation number 3. Now, we have 3 equations and 3 unknowns, namely A, D and E. Solving for A, D and D using these 3 equations, we get A equals 10.36 kilomoles, D equals 5 kilomoles and E equals 1.79 kilomoles. So, we have been asked to calculate the amount of trichlorosilane which is produced. So, that would be stream E. So, we get 1.79 kilomoles of trichlorosilane being produced per 100 kilogram of silicon which is fed. Converting this to mass, we will just have to multiply this with the molecular weight. So, molecular weight of trichlorosilane would be HSiCl3 is 1 plus 28 plus 3 times 35.45, giving you a value of 135.35 kilograms per kilomole. So, this means E equals 1.79 times 135.35 equal to 242.28 kilograms. So, for every 100 kilograms of silicon which is supplied, you end up producing 242.28 kilograms of trichlorosilane. With this, we have calculated what has been asked for in the problem. Now, let us move on to the next problem. Sodium hydroxide is usually produced from common salt by electrolysis. The essential elements of the system are shown in the figure. What is the percent conversion of salt to sodium hydroxide? How much chlorine gas is produced per kilogram of product, and per kilogram of product how much water must be evaporated by the evaporator. So, if you look at the flow chart, what you see is you have an electrolysis system which is the reactor in our case. So, the salt solution which is fed to the electrolysis system is reacted to form sodium hydroxide and chlorine and hydrogen. So, you have salt solution which is prepared using a dissolver. Before the salt solution is fed to the electrolysis system, the salt and water are mixed in a dissolver to produce 30% salt solution, which then enters into the electrolysis chamber and gets electrolyzed to produce sodium hydroxide. Then the sodium hydroxide solution which you end up with is sent to an evaporator to get a desired composition, which is given as 50% sodium hydroxide, 7% NaCl and 43% water as the product. So, now that we have the system, let us look at how we solve this problem. First thing we need to identify here is, although the process and the system has been given, The chemical reaction itself has not been given to us. However, we have been given what the reactants are and what the products are through the flow chart that has been provided to us. So, you have salt and water entering into the system, which means those two are the reactants, and you have chlorine, hydrogen and sodium hydroxide leaving as products, in addition to unreacted water and NaCl. Taking these into consideration, let us build the chemical reaction which would happen inside the electrolysis system. So, you have NaCl reacting with water to form NaOH plus chlorine plus hydrogen. Now that you have this equation, you need to verify if it is balanced. What you would see is it is not. Hydrogen and oxygen are not balanced. So, how do we go about this? To make sure that hydrogen is balanced, we can have a 2 here and here, thereby you have 4 atoms of hydrogen entering and 4 atoms of hydrogen leaving through the product stream. So, now you have 2 atoms of oxygen and 2 atoms of oxygen. However, sodium is not balanced here. So, you add a 2 here, thereby you ensure that sodium and chlorine are also balanced. So, 2 atoms of Na, 2 atoms of Na here, and you have 2 atoms of chlorine entering here and 2 atoms of chlorine leaving here. You have 4 atoms of hydrogen entering and 2 plus 2 atoms of hydrogen, which is 4 atoms of hydrogen leaving, 2 atoms of oxygen entering and 2 atoms of oxygen leaving. So, this is the balanced equation which we need for performing the material balance calculations. So, the next step is to identify the basis for the problem. So, the problem repeatedly asks for different information based on 1 kilogram of product being produced. So, taking that into consideration, we will assume the basis to be 1 kilogram of product stream which has been formed. So, the basis for the system would be 1 kilogram of product. So, this means you have 0.5 kilogram of NaOH, 0.07 kilograms of NaCl and 0.43 kilograms of H2O in the product stream. So, now for the first question is to identify the conversion of NaCl. For this, we need to know how much of NaCl is entering the system. We already know the amount of NaCl leaving the system. If we know how much of NaCl is consumed, then we can calculate conversion. The amount of NaCl consumed can be obtained by knowing the amount of NaCl entering and the amount of NaCl leaving. So, for this reason, we will start with an NaCl balance. So, NaCl balance would be input minus output plus generation minus consumption equals accumulation. At steady state, you do not have any accumulation. NaCl is a reactant, it is not being produced, so there is no generation. So, you end up with input equals output plus consumption. So, we need to calculate consumption. So, in consumption equals input minus output. So, now how do we go about calculating the consumption and the input terms? So, the consumption term would be equal to the generation of NaOH. So, that is what your stoichiometry says. Based on the reaction, 2 moles of NaCl consumed will result in formation of 2 moles of NaOH. You know that 0.5 kilograms of NaOH is produced in the final product. So, this means we can calculate the consumption of NaCl using the number of moles of NaOH produced. Consumption of NaCl is therefore equal to generation of NaOH. So, generation of NaOH is equal to 0.5 kilograms, which is equivalent to 0.5 divided by 40, which is 1.25 times 10 power minus 2 kilomoles of NaOH. So, therefore, consumption of NaCl would also be equal to 1.25 0.25 times 10 power minus 2 kilomoles. Now that we have the consumption term, we can calculate the input term as soon as we identify the output. We already know that the output for NaCl 0.07 kilograms. So, this is equivalent of 0.07 divided by 58.45, which is the molecular weight of NaCl, giving you 1.2 times 10 power minus 3 kilomoles of NaCl, which is leaving the system. So, your input is equal to output plus consumption, which is 1.2 times 10 power minus 3 plus 1.25 times 10 power minus 2, giving you 1.37 times 10 power minus 2 kilomoles being fed. So, now we have the input and the output terms and the consumption term for NaCl. If you recollect the definition for conversion, it is the amount of a reactant consumed divided by the amount of the reactant fed. So, based on that, conversion would be NaCl consumed divided by NaCl fed. So, here we have been asked for percentage conversion, which means this multiplied by 100. So, we know that NaCl consumed is 1.25 times 10 power minus 2 and NaCl fed is 1.37 times 10 power minus 2 times 100, giving us the percentage conversion as 91.2%. So, with this we have calculated the percentage conversion of NaCl in the system. The next part of the problem asks us to calculate how much chlorine gas is produced per kilogram of product. So, we need to identify the amount of chlorine which is leaving through the electrolysis system. If we have go back to the balance equation, chlorine would look like chlorine balance would look like input minus output plus generation minus consumption equals accumulation. No accumulation at steady state. Chlorine is a product, so it is not consumed. You do not have any input for chlorine, so thereby output is equal to generation. All we need to do is identify the generation of chlorine. So, if we look at the stoichiometry, what we identify is for every 2 moles of NaCl consumed, you have 1 mole of chlorine produced. So, you have 2 kilomoles of NaCl consumed produces 1 kilomole of chlorine being produced. This would mean 1.25 times 10 power minus 2 kilomoles of NaCl consumed would result in the formation of 1.25 times 10 power minus 2 divided by 2 kilomoles of chlorine, which is 0.625 times 10 power minus 2 kilomoles of chlorine. And if we were to convert this to mass, we will have to multiply this with the molecular weight for chlorine, and that would give us 0.625 times 10 power minus 2 times 2 times 35.45, giving us a final value of output for chlorine would be 0.44 kilograms. So, with this we have calculated the amount of chlorine which is produced in the system per kilogram of product being formed. To calculate the amount of water leaving the evaporator as water vapor, we need to perform a water balance. We also need to identify what would be the ideal system to work with. So, until now we have been using the overall system to perform the balances. It did not matter that we did not have information of the amount of water entering, because we were writing a balance for NaCl and for chlorine, and all the information we needed could be derived from the stoichiometry and the information about the product stream. However, to know how much water is actually entering the dissolver, we do not have any information, but we do have the information about the composition of the salt solution entering into the electrolysis system, which means we need to now identify a new system to perform our balance equations. Instead of considering the overall system, we can write the balance equation for the electrolytic system plus the evaporator. So, for this particular system we have chosen, we have information about the input stream which gives us the composition of NaCl and water, and we have information about the product stream which again gives us information about the composition of water present in the product, and in addition we have a product stream which is water vapor which is leaving the evaporator. So, we need to calculate this particular value. Now, let us start writing the water balance for this particular system. The water balance would be input minus output plus generation minus consumption equals accumulation. No accumulation at steady state. Water is not being generated as it is a reactant, it is only being consumed. So, you are left with input minus output minus consumption equals 0. So, this output term has two different outputs. You have one in the form of water leaving through the product and the other which is the water vapor leaving the evaporator. So, we will convert this into input minus output 1 minus output 2 minus consumption equals 0. Now, we need to know how much of water is entering into the system. What information do we have? We know the amount of NaCl which is entering the system. We already did this calculation, and the amount of NaCl entering the system is 1.37 times 10 power minus 2 kilomoles. So, this would be 1.37 times 10 power minus 2 times 58.45 kilograms, which is 0.8 kilograms of NaCl. We know that the stream which is entering into the electrolysis system is 30% NaCl. So, which means the remaining 70% would be water. So, H2O input to the system, water input to the system would be equal to 0.8 divided by 0.3 times 0.7, which is 1.87 kilograms. So, with this we can calculate the amount of water entering into the system. We now need to identify how much water has been consumed by the reaction. If you look at the reaction stoichiometry, you would identify that for every mole of NaCl reacted, 1 mole of water has also reacted. So, it is given as 2 moles of NaCl plus 2 moles of water reacting. So, based on that we can identify that for 1.25 times 10 power minus 2 kilomoles of NaCl reacted would mean that you have 1.25 times 10 power minus 2 kilomoles of water also consumed. So, this would mean that 1.25 times 10 power minus 2 kilomoles of water, which weighs 0.225 kilograms of water, has been consumed. So, we now have information about the water which is entering and the water which is consumed. We need to identify how much water is leaving the system. So, the water which is leaving the system in the form of the product is O2, which is 0.43 kilograms. So, based on this we have all the information. We have input, we have output 2, and we have the consumption. We just need to calculate output 1. Output 1, which is the water leaving in the form of water vapor, would be input, which is 1.87 minus output in the product stream, which is 0.43 minus consumption, which is 0.225, giving you the total amount of water evaporated as 1.215 kilograms as the water leaving the evaporator in the form of water vapor. With this we have solved this problem and identified all the basic information that has been asked for. In the next class we will look at a relatively more complicated problem with multiple processes and multiple units, and we will try to read the problem statement and draw up the flow chart which would be then used for performing the calculations. Thank you.